This is another method for the synthesis of inorganic material, that is microwave synthesis. When microwave fall on the liquid and solids, how they heat up liquid and solid. Microwaves are the waves which have very small amount of energy. So how they heat up liquid and solids. But before going to liquid and solid, we will discuss gases. Gases, microwaves can easily heat gases. How? Gases molecules are far apart to each other and they can freely rotate. Gases molecule can freely rotate. When microwave fall on the gas molecules, gas molecule rotation is increased, and in this way the gas molecules are easily heat up. But in case of liquid and solids, the molecules are not free to rotate because they are bound to each other through attractive forces. So how microwave will heat up liquid and solid? They will not heat up liquid and solid by rotational transition or by increasing their rotation, because liquid and solid molecules cannot rotate freely. So there are some other mechanisms how microwave heat up liquid and solid, and how we can prepare inorganic material to microwave synthesis. In a liquid and solid, the molecule or ions are not free to rotate, and so the heating is not the result of absorption of microwave by molecules undergoing rotational transition. In solid or liquid, the alternating electric field of the microwave. Whenever there are microwaves, they have alternating electric field of microwave. This alternating electric field of microwave will interact with the liquid and solid molecules, and how it heat up liquid and solid. In two ways, this alternating electric field of microwaves act in two ways. If there are two possibilities in cases of liquid and solids, if charged particles are present, and these charged particles can move freely. Charged particles are present and these charged particles can move freely. How alternating electric field will act on these charged particles which can move freely? These charged particles are present in solid or liquid. When alternating electric field is acted upon on these charged particles which can move freely, these charged particles will move under the influence of the field, producing an isolating electric current. So due to movement of charges, electric current will be produced. For example, there are free electrons, and due to movement of free electron in the presence of this alternating electric field, due to movement of these free electron, electric current will be produced. But this is alternating electric current, so isolating electric current will be produced because the electric field direction is changing periodically. When charged particles they move, and here is a case of solid and liquid. So when these charged particles move, they face resistance. Other molecules slow down in their movement due to resistance, due to friction. Resistance to their movement cause energy to be transferred to the surrounding as heat. So these charged particle movement resistance will cause production of heat, and this is conduction heating. And here is the second possibility. If no particles are present that can move freely, then how the alternating electric field of microwave will act on these particles? Molecules or units have dipole moment. For example, water has dipole moment. So if water molecules are present, one part of the water molecule is partial positive, other molecule of water molecule is partial negative. So how microwave will act on such type of solid or liquids whose molecules whose charged particle who cannot move freely, but the molecules have dipole moment. What will happen? Electric field, the alternating electric field of microwave. This microwave electric field will act on these dipole moment, molecules having dipole moments, and what will it do? It will align the dipole moments. It will align the molecules. Like here, these molecules are dipoles. So these molecule will rotate itself toward the this is the positive side of electric field, this is the negative side of electric field. So the partial negative side will rotate towards the positive plate, and positive side will rotate towards the negative, and in this way all molecules will align in the presence of alternating electric field of microwave. This effect produces dielectric heating, and when it acts on the water molecule in food, it is generally responsible for heating cooking in domestic microwave oven. So in the above case, what type of heating was produced? Conduction heating. And in this case, what type of heating is produced here? Dielectric heating. The electric field of microwave radiation, like that of all electromagnetic radiation, is isolating at the frequency of the radiation. So in all electromagnetic radiation, the electric field is continuously isolating. In the same way, in the microwave, the electric field is continuously isolating. The electric dipoles in the solid do not change their alignment instantaneously, but with the characteristic time t. Look, due to this isolation, for example, dipole moment first align like this. This is a dipole, positive pole upside and negative pole downside. Then due to isolation, the external electric field changes its direction. Its external field becomes in opposite direction. Now what will this dipole do? This dipole will also reverse its direction, negative upside and positive downside, and continuously the electric field is isolating, and continuously this alignment will be disturbed. The electric dipole in the solid do not change their alignment instantaneously. They change their alignment, that is positive towards negative. They rotate in the way that negative is upside and positive is downside. They do not change their alignment instantaneously, but a time is required, which is tough for changing their alignment. If the isolating electric field changes its direction slowly so that the time between the change is much greater than tau, then the dipole can follow the change. A small amount of energy is transferred to the surrounding as heat each time the dipole realign, but this is only a small heating effect. This is alignment, this is a new alignment, so each time a new alignment will take place, a small amount of heat energy will be transferred to the surrounding, but this is only small heating effect. If the electric field of radiation oscillates very rapidly, and this is the true case, electric field isolate very rapidly, but dipole cannot align very rapidly. Dipole cannot respond fast enough and do not realign. Dipole realign slowly, but the electric field isolates very rapidly. That is the true case. The frequency of microwave radiation is such that the electric field changes sign at a speed that is means it changes its direction from positive to negative. It changes its sign, and which is at a speed that is the same order of magnitude as tau. Here is another possibility, that is the time which is required for changing the alignment of the dipole. The electric field changing sign time is the same. Under these conditions, the dipole realignment lags slightly behind the changes of electric field, and the solid absorb microwave radiation. What will happen in this case? In this case, the the microwave electric field changes its sign, that is it changes sign from positive to negative or negative to positive, and realignment remains slightly behind, because realignment is mm, somewhat slow process. Behind the change of electric field and the solid absorb microwave radiation, and this absorbed energy is converted to heat. So the realignment takes place slowly. Electric field isolation takes place firstly, and in this way the molecule absorb microwave radiation because they not rapidly realign, and in this way the absorbed energy is converted to heat. To use microwave heating in solid state synthesis, at least one component of the reaction mixture must absorb microwave radiation. Because when one component will absorb the microwave radiation, it can heat up all the components, because when heat is produced, it will be transferred to the surrounding. So at least one component should absorb microwave radiation, or one of the reactant must absorb microwave radiation. Otherwise, if all the components are not absorbing microwave radiation, then the system will not be heated up. For example, if we are um, performing the experiment, we are sensitizing a material and we are using the solvent water. The water is a dipole, and water will absorb microwave radiation. The non-polar compounds will not absorb microwave radiation, and they cannot be heated by microwaves. The speed of the reaction process is then increased. How we can increase the speed of the reaction process? By increasing the rate of solid state reaction. Uh, Solid state reaction speed we can increase, and then we can increase the rate of whole process, and we can increase the rate of diffusion of reactants to each other. When reactant will diffuse to each other, then product will be formed very fastly, and this diffusion is the rate limiting step. If the diffusion is slow, mean mixing of the reactant is slow, then the rate will be slow. So the reaction process can be increased by a rate of solid state reaction by increasing the rate of diffusion. High temperature superconductors like these compounds, which is ytterbium, barium, copper oxide. This compound and other superconductors can be prepared by microwave synthesis. This compound can be prepared by ceramic method, but ceramic method require a very long time, that is 24 hours. And by microwave method, we can prepare it in just 2 hours. So here is the procedure. There are steps which we will take in this reported method. A stoichiometric mixture of the copper 2 oxide. We will take 3 reactants: copper 2 oxide, second one is barium nitrate, and third one is yttrium oxide. And we will take all the 3 reactants in solid form, in powder form, and they will be mixed to each other, and they will be placed in microwave oven which had been modified to allow safe removal of nitrogen oxide from formed during the reaction. So here nitrogen is present, so oxides of nitrogen will be formed, and the microwave is designed to remove the safe removal of nitrogen oxides. First, the mixture will be irradiated by microwave for 5 minutes, and 500 watts of microwave radiation, and the mixture will be treated with this radiation for 5 minutes, and then reground. Reground mean we will take out the material after 5 minutes and again crush this powder to more fine form, and then again we will put in the microwave radiation, and now the power of microwave radiation will be 130 to 500 watts, and the time will be how many minutes? 15 minutes. And finally, after 15 minutes we will take out the mixture and ground it again. We will crush it again, and then expose to the microwave radiation for 25 minutes. Okay, the microwave in this example, coupled to copper 2 oxide, all the materials cannot absorb microwave radiation. They cannot be heated through microwave radiation. So here in this example, which compound will absorb the microwave radiation. Microwave coupled with a copper 2 oxide, and copper 2 oxide is responsible for heating of all the reactant. This is one of the range of oxide mostly non-stoichiometric. This copper 2 oxide is non-stoichiometric oxide which are efficiently heated by microwave radiation. For example, a 5 to 6 gram sample of copper oxide, a small quantity of copper oxide, and when it is subjected to 500, when it is exposed to 500 watts of microwave radiation, for how much time? For half a minute, for only half a minute. It can attain such a high temperature during this half a minute, 1074 Kelvin. Other oxide which strongly absorb microwave radiation. Example of other oxides which can absorb microwave radiation. What are examples? Zinc oxide, vanadium pentoxide, manganese oxide, lead oxide, and so on. These are strong absorbers of microwave. By contrast, a 5 to 6 gram sample of calcium oxide exposed to 500 watts microwave radiation only attained a temperature of 356 Kelvin after half an hour. So some materials can increase the temperature to very high level, while other materials cannot increase the temperature to very high level. Other oxides which do not absorb strongly include titanium oxide, cerium oxide, iron oxide, and so on. They will not be heated by microwave because they will not absorb microwaves. Although microwave senses dramatically decreases reaction time, it does not solve the problem of chemical inhomogeneity and temperature in the reaction are high. So here are some of the drawbacks of microwave senses. Microwave senses have, what is the advantage? First, advantage is it has decreased reaction time. In a very small time, we can complete the reaction. But the product that will be formed will not be homogeneous. It will be inhomogeneous. And the temperature in the reaction are high, and some of the material will decompose on such a high temperature. So these are two drawbacks of microwave senses, that the material, the final product will not be homogeneous, and the very high temperature will be required for the synthesis. It does not have some other advantages, however. uh, One advantage is that less problem occur with cracking because the heating is from inside and not absorbed from outside. Cracking means the on higher temperature, large size molecules are converted into small size molecules. So there is less problem of cracking of molecules because heating is done from inside and it is not absorbed from outside. Molecules, due to molecular vibration and molecular friction, heat is produced. Increased homogeneity can be obtained with the hydrothermal method. This is the next method we will study, and which is used for obtaining a highly homogeneous product. This is another method for the synthesis of inorganic material, that is combustion synthesis. It is also known as self-propagating high temperature synthesis. In the combustion, there is always high temperature, and self-propagating means the reaction proceeds towards the final product by itself. Combustion synthesis uses highly exothermic and even explosive reactions. By the combustion synthesis, we can proceed through highly exothermic and highly explosive reaction, and to maintain for this reaction there is maintenance of self-propagating high reaction temperature. And for those reaction which has delta H value smaller than minus 170 kilojoule per mole, for those reaction which are highly exothermic reaction, and we can use this combustion synthesis method. It has been used to prepare many refractory material including borides, nitrides, oxides. Refractory materials are those materials which can withstand high temperature. Like these intermetallic ceramics, the reactants are mixed together, formed into a pellet. The reactants are not in the powder form, they are in pellet shapes, and then ignited. And for the ignition, The energy is used from laser, electric arc, heating coil, and at high temperature, ignited at high temperature. Once ignited, the reaction propagates as a wave because it is a self-propagating mechanism. The synthesis wave through the pellet and the reaction must lose less heat than it generates. It is self-propagating, so first time it is ignited. Like the burning of methane gas is self-propagating. First we ignite the methane gas and then enough heat is produced for the propagation of reaction. So here in the same way, the reaction must lose less heat than it generates. Means it should be exothermic reaction. The amount of heat generated should be high so that the reaction can propagate by itself, or it will quench. Temperature up to 300 Kelvin are maintained during the fast reactions. Means if quench means if there is more loss of heat and the generation of new heat is less, then the reaction will be stopped. It will not self-propagate. So loss of heat will be less and generation of heat will be more during this reaction. Means it should be highly exothermic reaction. Temperature should be such high that due to generation of this high temperature should be up to 3000 Kelvin are maintained during the fast reactions. Thermal ignition of a mixture of here is the synthesis method by combustion method. We take these reactants and we prepare this compound, that is barium iron chromium oxide, and this is non-stoichiometric compound. We can prepare it by combustion synthesis. The reactant used are barium oxide, iron oxide, and chromium oxide, and a pure iron. So such type of ferrite is produced after combustion. In the presence of magnetic field, the reaction proceeds faster and with high temperature propagation wave. So external magnetic field will cause the reaction to proceed faster because these are magnetic materials, iron, chromium, and these will interact with the external magnetic field. Example of other useful product of these reaction are hydrides for hydrogen storage. We can prepare magnesium hydride through this combustion synthesis. We can prepare titanium boride through this combustion synthesis. The magnesium hydride is used for hydrogen storage, hydrogen gas storage, and titanium boride is used for as abrasive and cutting tool because it is very hard. For the synthesis of carbide, we can use combustion synthesis, and silicon carbide, titanium carbide. What are the applications? For abrasive it is used, and as a cutting tool these are used. High pressure methods. High pressure method fall into three main categories: high solvent pressure in an autoclave, the hydrothermal method, which we'll study in the next lecture, using a high pressure of a reactive gas and directly applied hydrostatic pressure on the solid. So high solvent pressure, it takes place in hydrothermal method. We can use high pressure of reactive gas, and we can apply high pressure, that is hydrostatic pressure, on the solid. Some solid state application need single crystal. The hydrothermal method increases homogeneity, and here we will study in detail the hydrothermal method in the next lecture. So hydrothermal method advantage is that the product will be homogeneous and low temperature will be required, and we can also grow single crystal, mean a very small particle size can be obtained by hydrothermal method.